I think my mic was off. Good afternoon, everyone. Thank you, Danielle. And today we'll talk about tools of the industry. And again, this is somewhat of an overview. We'll talk more about some of these tools in more depth in some of the future lessons. So we do get data of various types and various scales. And some of the data is what I would call mega regional. And it goes down to very fine scale where we might be looking at a single portion, a certain compartment of a reservoir. So going down the scale axis, we do regional analyses to understand particular basins and how they interact or relate to other basins. We do a particular basin analysis. Within that basin, we may be interested in several blocks, or we may have licenses to explore on several blocks. Within that block, we may have 2 or 3 or 6 or 10 prospects. If we drill and find an economic quantity of hydrocarbon, we'll start to develop the field, and so we will want to study things on a field scale. And then, as I mentioned, the field may have several different reservoir compartments, and a person might be assigned a particular compartment to try to better understand it and maximize production from that compartment. At the mega regional scale, we have various types of data and tools, a variety of different types of geological maps. We are very interested in plate tectonics and how the particular basin that we're looking at formed and filled with sediments. We can collect gravity and magnetic data and get information on the basin in that fashion. Normally, we'll have at least regional seismic lines. As an area is explored more and more, we'll have more detailed local seismic. We may have just 2D grid of lines, or these days, most areas that are actively explored and developed and produced have 3D seismic data. We'd be interested in the tectonic evolution of our area of study, our basin or series of basins. We'd have a stratigraphic chart that we would assemble. We would try to develop some paleogeographic maps so that we can understand what type of deposition we might have had at various periods of geologic time. The mega regional analysis can be performed to decide which basins on the planet hold the highest potential for the discovery of hydrocarbons and then the production of oil or natural gas. I believe there's over 700 sedimentary basins, and even a company as big as ExxonMobil or Shell do not have the staff to monitor all 700 sedimentary basins. So every company is interested in high grading which areas they want their people to be studying. We may have an area, a basin that we're interested in. We think it has a lot of potential. If some blocks come up for bid, then we would want to determine which blocks of the ones that are offered might we want to bid on. And eventually we'll have to decide how much of a bid in terms of dollars we would place on each of those blocks. Also get a regional setting for the basin or the sub-basin that we're interested in to try to help understand the larger geological context and the characteristics of that particular region. And if we have a field that is in production, we may want to drill what are called step-out wells. Those would be wells nearby within, say, 10 or 15 miles that might have a similar set of conditions so that there may be some undiscovered hydrocarbon near our producing field. For local data, we have a surface type of data that would be topographic or bathymetric maps. We would have maps about the surface geology, and that would show us elements of the structure of the area and the stratigraphy of the area. We might be in a basin that on the fringes of that basin outcrop, and so we could study the outcrops and try to gain knowledge about the different sedimentary formations that we're interested in the center of the basin where we might have a reservoir or source. We have interest in understanding the heat flow history of an area so that we can understand and model hydrocarbon generation. Perhaps there's hydrocarbon seeps in the area. That is important as well. So I have two figures here. One is an outcrop. This is from West Texas. Of course, outcrops are a great place to look at ancient rocks, and the more they're related to what we're trying to explore or develop or produce, the better. And then on the right is a measured section, a tool that stratigraphers, sedimentologists use quite often. And we'll talk more about measured sections in a future lesson. We can also have subsurface local data, and there's two basic types. We get subsurface information when we drill wells, and from those wells we can recover cores or cuttings or logs. We'll talk more about those a little bit today, and then again in lesson number 4, which will be next Tuesday. And those types of data, cores, cuttings, logs, tells us something about the lithology, the geological ages, the geochemistry, and a various assortment of other physical properties about the rocks and the fluids. The other basic type, in addition to well data, is geophysical data. And the workhorse in terms of geophysical data for oil and gas is seismic. That can be a 2D seismic grid. It could be a 3D volume, or we also have the ability to collect what is called 4D or time-lapse seismic. That is where repeat 3D surveys are compared to each other to try to understand how fluids, particularly hydrocarbon fluids, have been moving as we've been producing the field. The other main type of geophysical data that we can collect is gravity data and magnetic data. So data from wells, the samples, we can get conventional cores, and I believe the next slide talks a little bit more about that. We can get sidewall cores. There's a slide coming up about that. And we can also get cuttings, and I have a slide about that. In terms of well data, we can also take measurements. We do that by lowering instruments or tools down into the hole, and each of these different tools measure different types of properties. So we can get temperature data, pressure data, fluid sample. We can collect fluid samples. We can get information on flow properties, and we can also get some seismic data using wells. Vertical seismic profiles, abbreviated commonly as VSPs, is something else that we can get. So this is a slide about conventional cores. The coring apparatus is positioned at the bottom of this drill stem, and so we punch into the undrilled formation at the bottom of the hole. Often we can get a meter or more of core. That is good for analyzing things such as lithology, sedimentary features, porosity, permeability, and paleontology, from which we can get the geological age and information about the environments of deposition by studying primarily microfossils. One thing to note, when we core, we have not yet penetrated the section that we're going to get the core from, so we don't have any logs, and so we're somewhat coring blindly. Oftentimes we will drill close to where we think the top of the reservoir is, and then we'll get a core, and if we're more than a meter or a meter and a half from the top of the reservoir, we may get a core that's a wonderful example of what the sealing lithology is, but we may not capture any of the reservoir lithology. The main drawback of conventional cores are that they are very expensive. To get a core requires 2 round trips of the drill stem. So wherever the well is cutting rock down at, say, 10,000 feet, Everything has to be pulled up. The core barrel has to be attached. Everything has to be lowered to get the core. Then everything has to be pulled up again to retrieve the core. And then the the cutting head has to be put back and lowered down. So that can be half a day, day and a half, maybe even 2 days to collect a core. Offshore drilling rigs in the exploration mode typically cost about $1 million a day. So if you need a day and a half to get a core, that core, irregardless of any other expense, is $1.5 million just for the rig time. We can also get what are called sidewall cores. They're small samples, about 1 by 2.5 inches. The diagram shows a tool that has about 30 of these little plugs. They are fired into the formation and capture a little bit of a sample. So on the right is a diagram showing the steps. Here's the tool on the drill stem. The yellow would be the formation on either side. An explosion occurs. It fires the little plug into the formation. It captures some of the sediment or rock. And then when they pull the drill stem up, they get that little sample of rock as well. We can also get cuttings, and cuttings you might consider as the rubble that comes up out of the well bore with the fluids that they circulate during the drilling process. We can get samples fairly easily. We can tell things such as lithology, or we can get microfossils and get paleontologic information on ages and depositional environments. The rock has been pulverized, so we can't get porosity or permeability information. We can't analyze sedimentary structures. It's very inexpensive because this is ongoing as they're drilling the well, and so there's no lost rig time. The problem with cuttings is that there's no real control on the depth for the piece of sediment that you're going to collect at the surface where the fluids are coming out. So hopefully it's come from the bottom of the hole, but how long has it taken for the fluid and the sediment to get from, say, 10,000 feet back up to the surface? The other thing is that the piece of sediment that you get may not be exactly from the bottom of the hole. Anything that is broken off, sloughed off a hole that has not yet been enclosed by cement or cased can contribute to the particular cuttings. We can also get measurements using a variety of tools. We generally talk about these as being wireline logs. Here's a display. This is a Schlumberger equipment. Here is where the cable is lowered down and brought up using a big drum. So the instruments would be attached, and then they can monitor how much of the cable has been played out, so they know the depth that the instrument is located at down inside the hole. We can get one or more physical properties, physical measurements, and that would be as a function of depth. And typically the data is shown as on the right. Depth is increasing down the page. Here are depth numbers. They're probably in feet, 10,450. And there are 3 different logs here, a gamma ray, resistivity, and a density. And we'll be talking more about logs in lesson number 4. This is a display borrowed from Schlumberger, and this shows several types of tools that can be lowered into the well bore, and each of these would collect a different type of data. They do not collect a single set of information with each run through the well bore. They'll couple 3 or 4 or 5 or 8 or 10 of these tools together. They register where each one is in depth relative to the cable, and so they can collect 8 different logs at the same time, and they're able to properly depth register each of the logs. The logs can measure the lithology and or mineralogy. Certain types of logs tell us the porosity of the formation. We can also interpret the fluid type and fluid saturation. We can get some information that we can use to try to estimate what the permeability of the formations are. We can get information on the stratigraphy, the rock types, the layering, where the major boundaries are, and with paleontologic information, microfossils, we can get ages. Some tools will measure pressure at different depths. We can get density, and we can get acoustic velocity. With the geophysical data, what we're trying to do is collect data at the surface that will give us an image of the subsurface. So a good analogy to surface seismic is a sonogram. And a common use of sonogram in the medical industry is to image a baby in the womb of a woman. And so here is an example of a sonogram. I do have a new son. I keep thinking I should get an image of one of his sonograms, but this is just off the internet. And they collect this by sending sound waves down into the woman's body. It reflects and comes up, and they have detectors. And by looking at the sound that goes down, comes back up, put together images that help them understand how the baby is developing. Well, we do similar things with surface seismic. So with surface seismic, we're going to have an energy source at the surface, and then we're going to have listening devices, and we'll have layering beneath us, sedimentary layering. So we'll have the energy source go off. This could be a stick of dynamite, common in the old days, not as common these days. It could be a series of vibrator trucks, or in a marine environment, it could be a series of air guns. So the energy goes down, bam, and we record the time after the shot. Listening device number 1 picks up a reflected energy at 0.4 seconds. Other energy goes down, hits the interface between layer 2 and layer 3. Some of it is reflected, and that listening device records energy coming in at 0.8 seconds. So if I do the animation again, bam, 0.1, 0.2, some energy reflects, most of it is transmitted, 0.3, 0.4, 0.5, some of the energy is reflected, most of it is transmitted, 0.6, 0.7, and listening device 2 records the reflection, the interface between layer 2 and layer 3. So if we look at what devices in the previous cartoon would record, we see the energy starting at 0.4 seconds for listening device number 1. That's from the boundary between the first and second layer. For device number 2, we see energy coming in at 0.8 seconds. That's for energy reflected at the interface between layer 2 and layer 3. And so we can build up images of the subsurface by using thousands of shots or explosions or vibration points and millions of receivers or listening devices arranged in a certain systematic pattern, either on land or in the offshore environment. Here's an example of the field data, a field record or a shot record. This is a marine environment. You can see that the energy has a hyperbolic shape. Those hyperbola are reflections off of different interfaces. And this goes down to 6,000 milliseconds or 6 seconds two-way travel time. We send our raw field data to the processing center. Our processing geophysicist will figure out how best to process the data to try to enhance the geological information and minimize anything else that we would refer collectively as noise. They generate images, and this is a cross-section seismic profile. This is the type of stuff I've been looking at for almost 40 years. And then we get seismic interpreters that will take the processed seismic and analyze it for faults and major depositional sequence boundaries and develop a geological history for the area of interest. The other type of geophysical data that we get is gravity and magnetic data. These instruments measure local gravity field and local magnetic field. The data have to be processed, and what we are usually looking for is not absolute gravity and magnetics, but what we call residuals. We look at the long-term regional response and filter that out and look for things that are more anomalous. And these can help us to identify and understand and interpret bodies either within the sediments or in the basement rock that have density or magnetic properties that are somewhat diagnostic. So the picture on the left is a Bouguer gravity map. Here's the coastline of Louisiana. This is the Mississippi Delta Birdfoot. And so that kind of shows you. And we can see these hot areas of high gravity. This is the same base map, but this is the magnetic intensity. And so these things can be used, in particular in this area, Gulf of Mexico, it would be used to try to understand how thick the sedimentary column is, or in other words, how deep basement rocks are. So that's my prepared statements. As I said, it's kind of an overview of some of the types of data that we will use. We'll talk more about log data in the next couple of lessons. And then there are numerous lessons on the different types of use of seismic data. So I will turn it back over to Danielle to see if there are some questions that the audience has raised.
Great. Well, thank you very much. Well, we have one question so far, but unfortunately it's related to lesson 2. Do you mind if I ask that one?
No, not at all.
Okay. So the question relates to faults acting like traps. So the question is, when do faults act like traps, and when do they act as migration routes?
The role of faults can be either it allows hydrocarbons to move through them, in which case the fault zone has to have a bit of porosity and permeability, or they can act as a seal in which they do not allow hydrocarbons to move. A lot of times the faults will behave differently depending on if we're talking about timescales of several million years, like hydrocarbons migrating into a trap, versus if we're talking about a time frame of 10 or 20 years when we're producing fluids. So we might have a fault that allows for the transmission, migration of hydrocarbons up to a trap, but then when we start producing from a field, we may find that that same fault acts as a barrier on the time scale of 10 or 20 or 30 years. And there's a lot of desire for people to be able to predict ahead of time which faults will act as conduits, which will act as seals. And there are several different methods that people use. We will be talking a little bit more about this. I don't have the list of lessons in front of me, but there is a lesson on migration and seal, probably around 7 or 8 or 9, that will talk a little bit about at least one of those techniques.
Great. And so we have a little, well, we have a question about if you could shed light on the cores. What exactly do the cores tell us about hydrocarbons? If you could elaborate a bit more on that.
Okay, let's see if I can get an image. So the core, if it's in pretty good condition, you can see visually different layering and sedimentary structures within the unit. That can tell us something about the depositional environment. We can take little samples and get porosity measures and permeability measurements. We can X-ray it. We can look at it in different type of lighting. And all of these different analysis methods will tell the sedimentologist stratigrapher different aspects about the rock. And it might be a core that's through the reservoir. That's probably the most common types of cores that we take, trying to understand how this particular rock would behave if we were to try to produce oil and gas out of it. Other cores are taken to look at seals and what the seal capacity, its ability to hold a column of oil or a column of gas in the subsurface. And we can also take core to try to get pieces of the source rock so that we can look at things such as the total organic carbon and also the hydrogen index, which is an indication of whether the source rock is going to give a lot of oil or only gas.
Great. We have a question about wildcat wells, and the question
Okay.
is, to drill wildcat wells, what level of scrutiny is given to the seismic interpretation of a regional seismic map? And also, are wildcats ever drilled from 2D seismic, or is it always 3D?
Okay. Before a wildcat is drilled, at least these days, there will be a lot of work done with seismic and with other data before the decision is made, yes, let's drill it. Typically, if we're talking offshore as an example, typically there will be a 6-month period in which bids are accepted for a particular block. And so you might have 6 or 7 people working 6 months to try to decide if one or more of the blocks are of interest. And so that's kind of the first pass or the first hurdle to get over to drill a wildcat. If a company gets a block, they may need to get more seismic data to get more detail, or they may have enough seismic from the bidding phase that they don't need additional seismic. But it's not unlikely for a seismic interpreter, or let me say a team of about 3, to spend another 6 to 9 months working on a prospect within a block that the company owns before they present to management where they would want to drill the first wildcat well. So we have, about a person year of effort in the lease sale phase, and we probably have 2 to 3 to 4 years of effort by a number of people before we would drill the wildcat. And then the question about 2D and 3D, that's somewhat dependent on the philosophy of the company that you would be working for. There are companies that will drill a wildcat well based only on 2D seismic data. There are probably not that many left that would be willing to take that risk. Most companies these days, before they would drill an exploration well, would require the acquisition, processing, and interpretation of a 3D survey. You have to remember the exploration well is going to be, say, $100 million, and they don't want to drill a bad well. So they'd rather spend money on getting seismic data and getting it processed and getting it interpreted so that they have a better handle on what's down there before they commit to drilling a wildcat well.
Great. That's a great answer. We have another question about how often are the sidewall cores collected for determining if a basin has a prospect, and how much are they compared to conventional logs?
The sidewall cores would probably be collected for some wells that are drilled in a subbasin. After we have a number of wells, they tend not to take either sidewall cores or conventional cores because they probably have some well information or sample-based well information, and then they have the logs. I'm not really comfortable to try to quote you how much it costs to get a conventional well or a sidewall core. I know the sidewall cores are relatively cheap because as you're coring a well, as you're logging a well, you can get the sidewall cores, so there's not very much rig time lost in collecting sidewall cores. As this slide says at the last bullet point, conventional cores are extremely expensive depending on how much time you tie up the drill rig and how expensive it is to have that drill rig waiting while the core is obtained.
Great. There's a question about seismic people who are seismic processors. So, do they usually do both? Like, do geophysicists work as both as seismic processors, and then they also do the interpretation of that work? Do they do both?
Yes, I understand the question. Most mid to large to super large companies, they have geophysicists that specialize in seismic data processing, and hopefully they understand what seismic interpreters do, but they probably wouldn't spend a lot of time doing seismic interpretation. If you're in a small company that might have, let's say, 10 geoscientists, then you may have to cover more bases, and you may have people that plan how the survey is going to be acquired. They do the processing, and then they do the interpretation. So usually it's more specialized. And I know of a number of cases where people have started in seismic data processing, and they're intrigued enough with the seismic interpretation that they retrain themselves and start to work as seismic interpreters. I know a few cases, not as many, where a seismic interpreter has crossed over and become a seismic data processor. My particular opinion is that in order to be a really good seismic interpreter, you have to understand at least some of the basics of what seismic data processing is all about, and that would help an interpreter understand the strengths and the weaknesses of the seismic data they've been given to interpret.
Oh, great. So kind of leading off of that question, what does the daily work of a geologist who's interested in well logs look like? Like what kind of opportunities within the oil and gas industry itself are there in positions?
There are quite a few people working in the industry that specialize in log analysis. Typically, the geologists would be able to do core analysis. They'd be able to do log analysis. They would use the cores to help calibrate what the logs are telling them. And then they would use logs from a series of wells, either on a mega regional scale or a regional scale or a block scale or a field scale, to correlate between the wells and try to come up with the stratigraphic architecture, the stratigraphic correlations, the stratigraphic history. So in my days at ExxonMobil, I would say there were probably as many geologists as there were geophysicists working for the at least the exploration part of the company.
Well, great, Fred. Well, with that, that concludes our Q&A time. And so just stay tuned for lesson 4, which is going to take place next Tuesday at 2 p.m. Eastern Daylight Time. And I hope you all can make it. So with that, this concludes the webinar. All right.
Thank you, everyone, for attending.
Thank you, Fred. All right. See you guys on Tuesday. Bye.
Bye-bye.